Homework 2.4, question 1. Question 1 says, well, do we have an exact ODE? Is 2x minus 1 dx plus 3y plus 7 dy equal to 0 is exact. Remember the definition of an exact ODE. For an exact ODE, if we have the differential form, m of x and y dx plus n of x and y dy equal to 0. If the partial derivative of m with respect to y is equal to partial derivative of n with respect to x, with the conditions that those partial derivatives, they are exist and they are continuous. If they are equal to each other, then we say that, hey, we have an exact differential equation. So m is 2x minus 1. The partial derivative of 2x minus 1 with respect to y is this guy equals to the partial derivative of n with respect to x. So with respect to y, here you have an expression in terms of x. So it means that this is just the constant when you're taking the partial derivative with respect to y. This is 0. On the right-hand side, you're taking the partial derivative of this expression in terms of y with respect to x. So this assumed to be a constant, which is 0 again. 0 is equal to 0. So the answer is yes. 2. The next question, number 5. So question 5, you have 2x y squared minus 3dx plus 2x squared y plus 4 and then we have dy equal to 0. dy equal to 0. Is it an exact differential equation or not? Again, the same process. The partial derivative of m with respect to y is this equals to the partial derivative of n with respect to x. So with respect to y, this is becoming 4xy. And the derivative of 3 is just 0. And with respect to x, we get 4xy. Are they equal to each other? Yes, they are equal to each other. So the answer is yes. Let's take a look at number 10. 10 says, well, here we have x cubed plus y cubed dx plus 3x squared xy squared dy equal to 0. The same process. Taking the partial derivative of m with respect to y is this guy equals to the partial derivative of n, 3xy squared with respect to x. So with respect to y, this is just 0. And then you get 3y squared. On the right-hand side, if you're taking the derivative with respect to x, it means that you end up with 3y squared. Are they equal to each other? Yes. So we have another exact differential equation. Now let us solve each one of these. The process is the same as process that we did in multivariable calculus. Since you have exact differential equation, it means that you can find a function like f of x and y, which is equal to the integral of 2x minus 1 dx. And if you take this integral, it becomes x squared minus x plus a function in y. Now, the partial derivative of f with respect to y must be equals to n. So since partial derivative of f with respect to y is equal to 3y plus 7, it becomes the partial derivative of this expression on the right-hand side with respect to y. So you're taking the partial derivative of x squared minus x plus gy with respect to y, which is 0, and g prime of y. So g prime of y is equal to 3y plus 7. So g of y is equal to 3/2 y squared plus 7y plus k. So your function is nothing but f of x and y. Let me write down the solution here for you. Equals to, we found some part of it, x squared minus x plus g plus 3/2 y squared plus 7y plus k. What about number 5? So our function f of x and y is equal to the integral of 2x y squared minus 3 dx, which is x squared y squared minus 3x plus a function in y. Now the partial derivative of f with respect to y is equal to, well, n, which is 2x squared y plus 4. Now we have to take the partial derivative on this side with respect to y, which is 2x squared y, and this is 0 plus g prime of y. So g prime of y is equal to 4, and g of y is 4y plus constant of integration, which is k. Now, if you substitute this back here, f of x and y, or the solution becomes x squared y squared minus 3x plus 4y plus k. Remember that in multivariable calculus class, we use this method to find the potential function. Here, f of x and y is equal to the integral of m dx. So we get x cubed plus y cubed dx, which is a fourth x to the fourth plus y cubed x plus a function in y. And now the partial derivative of f with respect to y is equal to n, which is 3x y squared. So the partial derivative of y of f with respect to y, this guy is 0 plus 3y to the second x plus g prime of y. So these two are equal to each other. It means that g prime of y is equal to 0, or g of y was just a constant line k. So if you substitute this back into the definition of f of x and y, you get a fourth x to the fourth plus y to the third x plus k. Let's take a look at 15 and 20. Well, question 15 says you have x squared y cubed minus 1 over 1 plus 9 x squared plus the parenthesis dx dy plus x cubed y squared equal to 0. Is it exact? Very well. So what do we have here? We have the differential form if we multiply everything by dy. So let me write dx and then dy equal to 0. We're going to write it in differential form so we can easily check to see if the partial derivative of m with respect to y is equal to partial derivative of n with respect to x. So the partial derivative of x squared y cubed minus 1 over 1 plus 9 x squared with respect to y is this guy equals to the partial derivative of n x cubed y squared with respect to x. So with respect to y, we can just completely ignore this term because it only has x in it. So on the left-hand side, it becomes 3x squared y squared. On the right-hand side, with respect to x, it becomes 3x squared y squared. They are equal to each other. So we have exact differential equation. And for number 20 says, well, I have this differential equation, which is 1 over t plus 1 over t squared minus y divided by t squared plus y squared, close the parenthesis, dt plus y ey plus t divided by t squared plus y squared dy equal to 0. So the partial derivative of m minus y t squared plus y squared with respect to y is this equals to the partial derivative of y e to y plus t divided by t squared plus y squared with respect to t. Okay. We need to check each of these partial derivatives separately and check to see if they're equal to each other or not. So here you don't have any y, it's going to be 0. This guy is also 1 over t squared, it doesn't have any y, it is 0. Minus, with respect to y, here you have a rational expression. So the derivative of y is just 1 times t squared plus y squared minus the derivative of t squared with respect to y is 0 plus 2y times y divided by, we take the denominator and raise it to the second power, t squared plus y squared to the second. So if you simplify this, you get negative t squared plus y squared minus 2y squared divided by this negative sign is outside, divided by t squared plus y squared to the second power, which becomes, so we get negative y squared, and here you have y squared minus t squared divided by t squared plus y squared to the second power. This is our left-hand side. We found the left-hand side. Now we have to move to find the partial derivative with respect to t here. Again, this guy only has y, so this becomes 0 plus, for the second expression, we have to apply the quotient rule. The derivative of t is 1 times t squared plus y squared minus, with respect to t, you get 2t times t divided by, take the denominator and raise it to the second power. If you simplify the numerator, you get t squared minus 2t squared, which is negative t squared. So you have y squared minus t squared divided by y squared plus t squared to the second power. Are they equal to each other? So obviously you see these two are equal to each other. So it is another yes for us. So now let us start finding the solution. The solution for the first differential equation, f of x and y, is the integral of x squared y cubed minus 1 divided by 1 plus 9x squared, and here with respect to x. So the integral of x squared to y cubed becomes a third x cubed y cubed, and here you're dealing with the arc tangent. you need to have 3 on the numerator, so it becomes a third inverse tangent of 3x plus a function in y. Now, if you take the partial derivative of f with respect to y, it must be equals to your n, which is x cubed y squared. So here, with respect to y, we get x cubed y squared, and this guy has no y in it, so it becomes 0 plus g prime of y. These two terms are equal to each other, so you can cancel them out. G prime of y becomes 0, or g of y is just a constant. So f of x and y, the solution becomes a third x cubed y cubed minus a third inverse tangent 3x plus k. Let's take a look at the second one, number 20. To find the solution, f of, you don't have any x, instead you have t, so f of t and y is equal to the integral of 1 over t plus 1 over t squared minus y divided by t squared plus y squared dt. Very well. So f of t and y becomes ln of absolute value of t minus 1 over t. And here, if you think about this, you have t squared plus a constant, and on the numerator you have your constant, so you're going to copy down negative y. And then if you just write this in terms of t over y, you can see that you have the arctangent of t over y. So I'm going to write this way: the integral of y divided by t over y squared plus 1. I just try to factor out y squared and dt. So f of t and y becomes ln of absolute value of t minus 1 over t. And here, if you simplify this guy, you get 1 over y, which is on the numerator, and you have the inverse tangent of t over y plus a function in y. Now, the partial derivative of f with respect to y must be equals to your n, which is y, e to y plus t divided by t squared plus y squared, which now equals to, we are taking the derivative of this with respect to y. This is going to be 0, and here you have a minus sign. This is going to be 0 again, and here you have the inverse tangent of t divided by y. Let's take the derivative. Here, with respect to y, it becomes negative t over y squared times 1 over 1 plus t over y to the second power plus g prime of y. So if you simplify this expression, and because of the negative sign that we have, let me see what we can do. Okay, it already has a negative sign and it has another negative sign, so we're going to plug that in. That becomes positive, so you can cancel out these two terms. G prime of y becomes y e to power y. So g of y, now you have to apply the integration by parts. So u is y, dv is e to y dy, du becomes dy, and v is e to y. So gy is equal to uv y ey minus the integral v du, which is just e to y plus a constant for your integration. If you substitute this back into the solution, f of t and y becomes ln of absolute value of t minus 1 over t minus inverse tangent of t over y and plus, let me erase this, plus gy, which is y e to y minus e to y plus k.